Algebra 2 7.7d, add or subtract complex numbers. Now we've got 21 videos for Chapter 7 so far, and 3 of them that were the previous ones before this one are really important if you haven't seen them, and there's links to them in this video's description. The complex numbers consist of all the sums of a plus b times I, where a and b are real numbers and I is the imaginary unit. You know, as I to the second power equals a -1, we talked about in the last few videos. So here's some examples of some complex numbers. 3 plus 2i, -5 plus 4.4i, 7i, because the value for a is 0 in 7i. So we don't have an a plus bi, we just have a 7i, that's the b and the I. If the a is set at a 0, well, that's still a complex number. So either part can be a 0. We could do a 5 plus 0 times that I. That's a 5, because we're adding a 0, aren't we? And if we have 0 plus 3i, well, that's 3i. The a is the real part, and the bi is the complex part. It's a real number times an imaginary number. And to have a complete number system, we define the sums of real and imaginary numbers as complex numbers. Let me move up here. We assume I acts like a real number, obeying the commutative, associative, and distributive properties. And when we add or subtract complex numbers, we treat that I like we would treat a variable. We combine like terms. So when we add two complex numbers, we get the sum of the real parts and the sum of the imaginary parts. I've got them stacked here so they're easier to look at. We have an a plus bi plus a c plus di. We add the a and c, and we add the bi and di. This is the real part. This is the real part times the imaginary part, and together it makes the complex number. So if we've got a -4 plus 5i plus a 3 plus 2i, we take our -4 and our 3 together, and we get a -1. We take our 5i and add it to the 2i, and we get a 7i, and that's our answer. If we have a 7i plus a 9i, we just add the like terms, and we get 7 plus 9i, which is a 16i. If we've got a -5 plus 6i plus a 2 minus 11i, we put the like terms together. We have a -5 plus 2, see? And we have a 6i minus 11i. That gives us a -3 plus a -5i. For this one, we get a -2 plus a 2. Well, that's going to make a 0, isn't it? That's an additive inverse. That's a 0 pair. And we have a positive 3i minus 3i. That's another 0 pair, isn't it? That's another additive inverse. So the whole thing equals 0. When we subtract complex numbers, we get the difference of the real parts and the difference of the imaginary parts. So now, when we have a subtraction sign in between them, what we're going to do is do a minus c plus bi minus di. See? We get the real part plus the real times imaginary. If we have a 2 plus 3i minus 4 plus 2i, we do a 2 minus that 4, which is a -2, and we do a 3i minus a 2i, which just gives us I. So we have a -2 plus I. If we've got a -4 plus 10i, and we're subtracting a -2 plus 3i, we can even stack them so that we can see them easier. When we have a -4 minus a -2, we add the opposite, don't we? So we're going to do a -4 plus 2. That's going to give us a -2. And we have a 10i minus a 3i. That's going to give us a 7i. So we have -2 plus 7i for our answer. This might be easier for you instead of doing it in sentence form. We have a -4i. So now we've got the imaginary part in the front, don't we? We have a -4i minus 3 minus 2i plus 5. If we stack them, we can see we have a -4i minus 2i. That's going to give us a -6i. We have a -3 minus a positive 5, that's going to give us a negative 8. So what we did was we took the negative 4i and we subtracted the 2i and got a negative 6i. We took the negative 3 and subtracted that 5 and got a negative 8. So our answer is negative 6i minus 8. So remember that you can stack them if that's easier on your eyes. I personally like that. I can go quicker. So complex numbers are an extension of real numbers. It's a plus the b times I. And real numbers, every real number, a, is a complex number because in this form, a plus b times I, if b is a 0, it's going to equal an a, isn't it? Because we're adding a 0. 0 times I is 0. And imaginary numbers, all imaginary numbers, b times I, are complex because b times I can equal a 0 for the a plus bi, which is just going to be the bi, isn't it? See? I'm going to add this video to the Algebra II playlist so you can study it. Our next video is 7.8a. We're going to do graphing of complex numbers. And in 11.6, we added and subtracted radical expressions back in Algebra I, but there's videos about that in this Algebra II playlist also. And the 3 previous videos where we talked about I, the imaginary number, were 7.7a, b, and c, and there'll be links in this video for that too, okay? So all you have to do is go to the description and click on the links, all right? I hope you're having a great day. I hope this was easy for you to understand, and I hope I'll see you next video. Don't forget to hit the like button if I helped you. Bye.